Hi there, everybody. It's SkepticMystic from the Obsidian forum and from the Discord. In this video, I'm going to be going over mine and Emile's plugin called Graph Analysis. So the first thing we'll need to do is just install the plugin. You can do that from the community plugin page. And you'll see that I've already got it installed, but using the default settings, and you can just enable it from there. So before we even look at what graph analysis can do, let's just consider what it's meant to do. So it's a plugin that allows you to see the results of various different graph analysis measures being applied to your Obsidian Vault. And that can sound like a lot. Basically, we're using some pretty fancy math in some cases to analyze like which nodes are most similar to one another, or try and find groups of nodes in some cases. But we'll see how that works. And the two main types of algorithms that we use are structural. These algorithms only consider the links in your Obsidian graph. They don't consider the content of the node. And the other kind look at what's inside the node. They compare the words inside the node to other node contents. Good. Just before I go any further, I just want to note that I'm using a publicly available vault, which you can find over here at this GitHub repository. I'll post a link to this in the description. Yeah, this vault has quite a few files in it and lots of useful links between them about a lot of different subjects. So you could use this to test your plugins, for example, or graph analysis. So let's enable or take a look at the results of graph analysis. So the main thing we're going to be using from the plugin is the graph analysis view. And to open that, we need to run this command, open graph analysis view. And you'll see on the right side, a new leaf appears, and it should look like this, depending on what page you're on in your vault. So let's just pick a random node, and we'll pick this algorithm to run. I'll explain these in a moment. Not all nodes are going to have results, but so language is a good one to use. So the note about language gives us all of these results to see. And this is a lot of information to take in. And so, as I've noted here, in a lot of cases, there are going to be a lot of numbers. Sometimes that's not the result of the algorithm. But what I want to show the importance of is that the exact values aren't like really what you should be considering. Most of the time, the relation between those values to other nodes in your vault is what gives you the most information. And we'll see how that plays out using some examples. Good. So I'm going to go over each of the algorithms available in graph analysis, except for co-citations. Co-citations is quite a big topic on its own. And so Emile, the resident expert on co-citations, is going to make a separate video just for that. Good. So with co-citations aside, there are a few different types of algorithms that I've grouped into these categories. The first kind I'll go over are link prediction algorithms. And a link prediction algorithm is taking the structure of your graph and saying, look at the current nodes, and for every other node, give me the probability or predict how likely it is that these nodes should be connected to each other, whether or not they actually are. Okay. So this is the result that I showed on the language node. So let's go back to language nodes. And we can see all of these results here. And what this is saying is that based on the structure of your graph, this is showing which nodes should be linked to the current nodes. Okay. So it's predicting quite highly that the nodes about humans should be connected to the nodes about language. And that sort of makes sense intuitively. And a helpful way to kind of gauge the result is to see if those nodes are actually linked. So if we see this little icon next to a result, that means that the nodes on language is actually linked to the nodes on brain. And we can see that over here, for example. This icon will appear bidirectionally. So if the node brain links to the node language, it will also appear next to the result there. Yeah, and we can gauge these results. Language and psychology are quite linked, for example. You can scroll through them. We can also sort the results in ascending or descending order. So of the results that weren't zero, logical connective is the least likely to be linked to language. You can also, we actually filter out zero. So this toggle isn't actually doing anything in this case. But yeah, it's nice to be able to sort the results in ascending or descending order and just jump around between the nodes. If we go to the nodes on humans, we can see it's most likely connected to the nodes on brain. If you hover over the results, we can see which nodes which nodes these two have in common. So this is saying that the nodes human and brain have common neighbors, developmental psychology, feeling, human brain, for example. And again, these will appear bidirectionally. So even though the human node has no links leaving it, the nodes on developmental psychology has a link going to human. And yeah, and we can see lots of results here. And they all kind of make sense. Good. So that's a link prediction algorithm. It's telling you how likely is it that the current node is connected to every other node. So let's go back to our starting page. We're done with link prediction. And let's take a look at similarity algorithms next. There are a few different ways you could kind of define this. My understanding is that, again, based on the structure of your graph, the links between your nodes and not the content in those nodes, a similarity algorithm is telling you how similar the current node is to every other node. So let's change over to the Jacquard similarity algorithm and go back to the Anki node, for example. And we can see that you can hover over the information icon to see a little bit more. Again, based on the structure, it tells you how similar they are. And a bit more in depth, this algorithm is showing you the ratio of the number of neighbors these two nodes have in common to the total number of neighbors they have together. So the maximum value could be as 1 and the lowest is going to be 0. And we can see all those results here sorted in descending order. But so the nodes on Anki is very similar to the nodes on Obsidian, and they are actually linked. It's very similar to the nodes on repetition suppression, and those aren't actually linked. So perhaps that's giving you a hint that those nodes are similar enough that there should be a link between them. Yeah. And again, we can jump around the nodes, control, hover to preview the nodes if it actually has content. Yeah, lots that we can do there. So those are similarity algorithms. You'll see that there's another similarity algorithm listed, but it's not shown here, even if you scroll. And that's because in the settings for graph analysis, not all of the algorithms are shown by default. There are quite a few, and it can be quite overwhelming. So we as the developers have chosen not to show all of them, but you can come here and turn some of them on. Co-Citations is shown by default, but not for this video. So if I turn on the overlap algorithm, the other similarity algorithm, if you refresh the index to make it appear here, you can then show the overlap algorithm and yeah, get an idea of the overlap similarity between nodes, for which I haven't given a description. So if you do want to see a bit more in-depth information about each of the algorithms, you can read the README on graph analysis. You can find it here on the repo. And we give quite a bit of information about each of the algorithms and the actual formula, like what is the maths doing for this algorithm. Yeah, and that can be quite a lot to take in. So mostly what I want to get across is an intuition for what each of these algorithms are doing. So again, this is a similarity algorithm telling you that like the cognitive strategy node has a high overlap similarity with the time node, for example. Good. So those are similarity algorithms. Let's have a look at centrality. A centrality algorithm is telling us, it's giving us an idea of which nodes are like most central if you sort of bring the most highly linked nodes to the center of the graph. These are going to tell you which nodes those are. So the centrality algorithm in graph analysis is HITS. If we activate that and jump to it here, we can see these results. Okay, so one thing to note, because it hasn't come up yet, is this little icon here. It's an icon of a globe or the Earth. And this is telling us that the HITS algorithm is a global algorithm. What that means is that it doesn't depend, the results don't depend on the currently focused nodes. So if I change nodes, you'll see that these results are just staying the same. It's a global algorithm. The results don't change based on which node you're currently focused on. And so the HITS algorithm is telling us the hub score and the authority score of every node in the vault, right? And so an authority is a node with lots of links coming into it. Lots of different nodes cite this node, and so it has a lot of authority. A hub is a node which has lots of links leaving it, right? And the HITS algorithm is showing us both of the scores in one. By default, it's sorted by authority in descending order, so we can change that to ascending order. We see that authority is all 0. And we can also change it to sort by the hub score in descending or ascending order. Right, so just using the default sorting, we can see that the node on brain has the highest authority. Most nodes link to the brain nodes. Yeah, bit of synchronicity there maybe. And it has quite a low hub score. Yeah, so this gives us a way to assess that. And if you change nodes, you can see if your the currently focused node is bolded in the results. Good. So these are some interesting ones. We also have, not that the others aren't, we also have community detection algorithms. The first of which I'll show is label propagation. But first, a community detection algorithm is taking the structure of the graph and using different methods based on the algorithm. It's saying, well, like this clump of nodes here forms a community. These nodes are more highly connected to one another than they are to the other nodes in the graph. And so they should form a cluster, a community of sorts, right? And we can sort of gauge that just by looking at the graph. Like there's a cluster over here, maybe one here, smaller one over here. But these community detection algorithms are giving us explicit communities. So let's look at label propagation. You'll see it's also a global algorithm. So the results don't depend on the currently focused node. And this is a lot to take in. This is the result of running a label propagation algorithm on your graph. I've given a description here. Basically, you give each node in the graph a label, which happens to be its own name. And then over multiple steps, multiple iterations, each node takes on the label of the most popular label among it. So at first, that's going to be quite a random process, but over time, certain labels are going to become more and more popular in the graph and sort of take over their given community. And after the specified number of iterations, which you can change, we see the community that each node landed up in. And so on this node on polyamory, for example, these ended up in that cluster. Let's take a look at a more popular. Yeah, so the nodes on happiness form quite a big cluster, and we can see based on this icon that the personality node is linked to the happiness nodes. And so that gives you a good idea of like the validity of that cluster, of that community. But even if the nodes aren't actually linked to the community nodes, the results are still pretty good, right? Like jealousy is relevant to like polyamory, for example. Yeah, and so the results are going to be different for your vaults, but it always kind of surprises me how accurate it is. And there's quite a bit that you can change. You can lower the number of iterations to 1. And based on the algorithm, if you only pass labels once, then by definition, all of the nodes in that community are going to be linked to the community nodes. Yeah. And so if the number of iterations is quite low, then you're going to have quite a few communities because it hasn't had a chance to, the more popular labels haven't had a chance to take over in a sense. And if we increase the number of iterations, then the happiness node has 517 nodes in its community. Good, and you can change the sorting order, for example. Yeah, so quite a fun one. I quite like the the label propagation algorithm. We also have the Louvain community detection algorithm. And this is doing something quite similar. It's also running a community detection algorithm, one that I don't quite know how it works. The coding library I use just implements it for us. And so we've added it to graph analysis. This is not a global algorithm, so it does depend on the currently focused nodes. And the Louvain community detection algorithm only shows you the community that the current node is in. Okay. It doesn't show the current node because it will always be in that community. Yeah, and there's a bit of randomness to it. So if you refresh index, sometimes the results will be different. Yeah, and you'll see that they're pretty accurate. Yeah, again, you can change the resolution. Fewer iterations makes for larger communities, and more iterations makes for more refined communities that are generally more accurate. And lastly, the clustering coefficient. This is a global algorithm. And this is kind of interesting. It tells you the likelihood that a node's neighbors are connected to one another. So this node on endorphins has the following neighbors. There's a bit of a bug there, but yeah. So this is showing the triangles that this node is a part of, but we can just think of that as its neighbors. And so it's telling us that there's quite a high probability that the nodes on endorphins, that node's neighbors are probably connected to one another. So happiness and pleasure are likely to be connected, for example. Yeah, and that likelihood sort of tells us about the node that it's connected to, about the nodes on endorphins. Yeah. So it's quite a different algorithm there. But yeah, something to play around with. Good. And before I show the last type, I haven't mentioned this frozen icon. It's a flame. And the frozen icon, so if we go to a non-global algorithm, because it's non-global, it depends on the currently focused nodes. So if we click around, the results are going to change. But sometimes you don't want those results to change. And so we can freeze it on the currently focused nodes. And that means that if you click around, it will change nodes, but the results won't change because it's still frozen on the node we froze it on, right? And then if you do want to unfreeze it, you can just click that again and the results will refresh based on the current nodes. That's a nice way to kind of keep the results, but still change nodes. And then when you want to, you can unfreeze it and the results will refresh. All right, so the last few algorithms that I'm going to show are natural language processing algorithms. And so all the previous algorithms that I've shown you are structural. They only consider the graph, the links between nodes. They don't consider the actual content in the nodes, right? But these natural language processing algorithms do. They look at like the actual words in the nodes and tell you things about them. A little caveat, the Co-Citations algorithm does consider content. It actually considers both. But yeah, that'll be a different video. And so to use these natural language processing algorithms, I'm just going to disable these other ones and just turn on those. In order to use these, you'll see that we need the NLP plugin. This is a separate plugin that I created, and we need its functionality in order to use the natural language processing algorithms in graph analysis. Okay. So the NLP plugin does a whole bunch of other things, but it also gives us a way to run these algorithms on our vaults. I'll uninstall it just to show how to get it using Brat. Okay, so the NLP plugin is not on the community plugin list. So you can either install it manually or you can use the Brat plugin, which is on the community plugin page. If we go to Brat, we can say add a beta plugin. And if you type this, the repository for the NLP plugin, Brat will install it for us as if it was on the community plugin page. It is quite a big plugin. Okay, so you'll see that it's been installed. Just going to refresh that, enable the plugin, and you'll see that we have it here. These don't matter right now. Actually, they do. So in the NLP plugin settings, if you want to use it with graph analysis, we need to turn this setting on. And yeah, so the reason I've kept it as a separate plugin is because this can take quite a while. You only need to do it once every time you start Obsidian, but waiting like 5 seconds every time can be quite a lot. And so it's not on by default. You only need this on if you want to use the NLP plugin with graph analysis. But yeah, just a warning that it can take a little while depending on the size of your vaults. All right, so I'm going to reload just to let the NLP plugin do its thing. Not sure why that got disabled. Sure, okay. So yeah, this now works. So we installed the NLP plugin, we toggled that setting on so that we can use it with graph analysis. And now we see each of these 3 algorithms will work. So let's go over each one of them. The bag of words analysis takes the content of a note, it splits it into its individual words, counts how many times each of those words appears, and then uses those frequencies to kind of calculate a similarity between notes. So if two nodes share a lot of words in common, then they can be considered more similar to one another, right? So for example, the graph analysis node is quite similar to the Monte Carlo method, which I think is pretty accurate, just based on the words in this note and the words in this note. Computational algorithms, yeah, lots of stuff related to the graph analysis nodes. Good. And it's, you can tell it's an NLP algorithm because of the little speech bubble. Yeah, and we can jump around looking at different notes. Good, so these are, again, I'll just point out, they're fundamentally different in that they're considering the content instead of just the structure of the graph. They're looking at the actual words in the notes. All right, the next one is, I won't say that, butcher it, but this is also a similarity algorithm, just like the Louvain similarity or community detection algorithm. I'm not sure what it's doing under the hood. The NLP library that I've implemented just offers it as a feature, and so I've implemented it here. But again, it's taking the content of the currently active nodes and every other note and comparing them, seeing how similar they are to one another. And again, we see, again, like pretty similar results. Monte Carlo method, we've got a different nodes at the top. The nodes on LaTeX, for example, is very similar to these nodes. And that does seem pretty accurate. Good. And lastly, we've got a sentiment analysis algorithm. This one can take a little moment to load. It's a global algorithm, so it just gives us a value for each note, not dependent on the current note. And this is running a sentiment analysis. Like the sentiment is a positive or negative, and yeah, giving that value to us. So a high value indicates more positive sentiment, a low value indicates negative sentiment. And so we can look at, in ascending order, the lowest note, the note with the lowest sentiment is on trauma. And that makes quite a lot of sense. We've got these notes about like anatomy, for example. There's a pretty bland, not a lot of happy words in there. Yeah. So these kind of make a lot of sense as well. Good, something to play around with. All right. So those are each of the different algorithms, different video for co-citations, but I've gone over every other algorithm. So I hope that like really helps give you an intuition for what it's doing. I know that it can be a lot to take in, but perhaps something helpful to note is that there isn't a lot of setup for graph analysis. You can just install it, open this view, and very quickly get going, start like seeing link prediction and similarity between your nodes. So there's not a lot that you need to do to start using graph analysis, but perhaps just overcoming the hurdle of like so much information coming at you. Right. So I'll just reiterate again, like the exact values aren't that important. Like it doesn't matter that this is 2.9047 and not 46, right? It's more just the relation between the nodes. So this node has a higher sentiment than this one, for example. Okay. And just before we finish, I'm going to go over the settings of graph analysis. So we've shown that you can choose different algorithms, and you can also choose a different one to show by default. It will only allow you to choose from the currently selected ones. So only now we can choose from all of them. And, there's the option to exclude infinity by default. I don't know if that actually happens anymore, so these might be outdated. Oh, this is really cool. So we can also include other files, not just markdown files in the vault. So this means like images, videos, PowerPoint presentations, whatever you can put in your Obsidian vault, graph analysis can analyze. Something that goes quite nicely with this is to show thumbnails for images. So if you do show if you do have all file extensions included, then showing the image can be quite cool as well. So for example, if we go to the note on road cycling, we can see now that images are being included. So this note on road cycling is deemed to be like relatively similar to the note on the different power levels. I'm not sure about cycling, don't do it myself, but yeah. So it can show the images, it can show any file extension that you have in your vault. You can hover over it to make it bigger, you can jump to the image. You can see results from an image's perspective. So this image is quite similar to these notes. Yeah, so even though these notes aren't connected to this image, these notes don't link to this image, graph analysis says that they're quite similar, which this applies to the other algorithms too. So this image is in this community on road cycling, which again is pretty accurate. This is to do with co-citations, so I'll skip that. You can include unresolved links, links which haven't been created. You may or may not want to do this. I think it's on by default. There are also two means of excluding notes from graph analysis. So if you don't want particular notes to be shown in the results, you can either exclude them using a tag. So you can say, don't show me notes which have the tag like cycling, for example. This vault doesn't have any tags in it, so I can't really demonstrate it. But yeah, you can use like cycling on the road, you can use nested tags, you can use multiple tags, so like soccer, for example. And any notes with these tags won't be included in the graph analysis results. Okay. And lastly, you can also exclude notes using a regular expression. Any file name which matches the regular expression will not be included. Okay, so we can see that the road cycling note appears quite highly here. And so I will exclude any notes which have cycling in the name. Importantly, the regular expression is being tested against the full file path of the note, not just the base name. So you need to include folders and the extension, which gives you a lot of control over the regular expression, but might be like a catch if you don't realize it. Sure, so let's do a regular expression live on air. So any folder, if the note includes the word cycling, yeah, then it disappears. Okay. So yeah, we can exclude notes using a regular expression and with tags, and that will hide them from here. I personally use that to exclude my daily notes, which I prepend or append DN to them. Yeah, so this will exclude that. Good. I'm going to finish there. Covered quite a lot, but it's actually basically everything. It's just co-citations, which Emile is going to make a separate video for, as I said. But yeah, there's so much that you can do with this plugin. I know that it's a lot, but it can be like really quite powerful. So yeah, have a play around with it, test it in your vault, and let us know what you think. It's always cool to hear about like interesting results and how you find it useful. Also, please let us know if you find bugs. We're always looking to squish bugs. Okay, cool. Yeah, here's the repo. Thanks a lot for listening, and I'll post any relevant links in the description. Cool.